Hello everybody, and welcome to the Bio107 section .04 and section .05 lecture with Mary Annarella, your host and instructor, coming to you sort of live, recovering from having my kidney stones crushed. That was a really good time. I am doing well, however, but I knew that I would not be able to come into work. My doctor said, nope, you need a couple of days to not be on your feet. I'm recovering nicely and will hopefully be stone free very soon. Anyhow, so I'm recording this lecture for you. I will see you again on Tuesday. Oops, need the pen. Tuesday, October 1st, same time, same place as usual for our first exam. So our exam number 1. None of the material in this recorded lecture will be on this exam, but please make sure, I will assume that you have listened to this lecture and taken notes from this lecture before we meet again on Thursday, October 3rd. So this is all new stuff. We're going to be talking about some of the old stuff because we need to talk a little bit about some old stuff where we left off on this past Thursday in order to talk about new things. So let's get started. We have been talking about lipids. And we had discussed simple lipids versus compound lipids. And you already have in your notes from last time, and it will be on your exam, that simple lipids are made up of carbon, hydrogen, and oxygen in no particular ratio. And an example of those were the fats, where you take a glycerol molecule plus a couple of fatty acids, and you get a simple lipid. You get a fat. Compound lipids have carbon, hydrogen, oxygen, plus some mystery element. All right. The example that we are going to talk about with the compound lipid is when the mystery element is equal to phosphorus. And what we get when we have carbon, hydrogen, oxygen plus phosphorus is the phospholipid. The phospholipid is hugely important in the structure of the cell membrane. In fact, phospholipids make up the entire cell membrane. Your cell membrane is made of gazillions of phospholipids. And what a phospholipid is made up of is, it's a diglyceride, which is a glycerol molecule with two fatty acids. Di means two, so two fatty acids attached to a glycerol makes a diglyceride, and you should know what that structure looks like by now because it will be on your exam. But a phospholipid is a diglyceride with a phosphate group attached to the third carbon. So let's take a look at what that looks like. Okay, our diglyceride is going to look like this. We're going to have a glycerol molecule, which is just 3 carbons with an alcohol group hanging off of each carbon. And then attaching a fatty acid here and a fatty acid here. Right, so the acid part of those fatty acids are going to look like this, a long carbon hydrogen chain. Right there. I'm not going to draw all those hydrogens. You can use our imagination for that. And a second one here. I'm not going to draw all those hydrogens either, but nothing but carbon and hydrogen down here. A dehydration reaction comes along and rips out an OH group from the fatty acid and a hydrogen from the carbon, from the glycerol molecule. Oh, I'm running out of space here. Oops. Had a nice little Instagram notification coming in there. Darn it, I should have shut those off. Okay, but pull out a water molecule there, and that's called a dehydration. So I'm gonna get rid of that, and now these babies are connected here, and we'll do the same thing there. Oops, keep getting these Instagram notifications. Okay, we'll dehydrate this here, and now these are connected, and here we have a diglyceride. This is a diglyceride. Okay, 1, 2 fatty acids attached to a glycerol molecule right there. For the phospholipid, instead of attaching a fatty acid molecule here at this third OH group here, a phosphate group is going to be added instead. This isn't working. Back here. Okay, phosphate group, let's make that yellow. Now remember that a phosphate group looks like this. It's a phosphorus atom attached to a bunch of OH groups. And an enzyme will come along and dehydrate them as well and take out those two hydrogens and 1 oxygen. And now they're going to be attached to each other. So a dehydration reaction puts those together too. Let me erase this water molecule. There we go. All right. Now here's the deal with this phosphate group. I know we usually draw it like the, letter P with a circle around it, but I want to show you something with it, that these hydrogens often get lost. They hop off, and this whole thing forms an ion, and each of these oxygen gets a -1 charge to it. All right. So we've got this phosphate group here with a negative charge on it. Is that going to be hydrophobic or hydrophilic? Is this going to hate to dissolve in water, or is it going to love to dissolve in water? Think about that for a sec. Is it going to like to dissolve in water or hate to dissolve in water? This is the part of the lecture where I would just wait for someone to come up with the answer, and somebody would go, oh, it's going to be hydrophilic because charged particles, like salts and stuff, like to dissolve in water. So yes, this is going to be very hydrophilic. We're back. I think when I hit decline, that somehow stopped my screen record. Stupid spam. I hate spammers. I hate spam. Anyhow, this phosphate group is going to be very hydrophilic. All right. But then think about all of these long carbon chains here. Down over here, okay, all these are just a bunch of hydrogens on them. Like that. This one, just nothing but carbon and hydrogen. And these are very non-polar bonds. Nobody gets any partial charges here. So these tails here, oh my gosh, they are going to be very, very hydrophobic. They're going to hate water. These long fatty acid chains, they are not going to dissolve in water. We hate it, precious. Whereas this phosphate group over here is going to love water. It absolutely is hydrophilic. So this molecule's got a problem. I mean, we've got this whole huge molecule up here that's got a problem. One end of it is hydrophobic, and this end of it is hydrophilic. And you know what? Hydrophobic stuff does not get along with hydrophilic stuff very easily. They don't like each other. All right, but they're part of the same molecule. So they're stuck with each other. What happens is that this phosphate group here, it's gonna spin around on this bond and get as far away from these hydrophobic tails down here as it can. And what will happen, get rid of that, is that this whole end of the molecule here will be what we call the polar head. That's where the phosphate group's gonna spin around and hang out on this end and get as far away from the hydrophobic tails as it can. Oh, I just gave it away. These long fatty acid chains, and I'm gonna make a mess here, we're just gonna draw like long lines, and we'll call these the hydrophobic tails. And from now on, when we draw the phospholipid, we're not going to draw all of this stuff here. We're going to draw the polar head that has the phosphate group that's negatively charged. And we'll draw these hydrophobic tails, just as kind of sort of wavy lines like that. So these are our hydrophobic tails, and this is our polar head right there. That is the phospholipid. We could even draw it like this. Like that. It looks like a jellyfish. Like a jellyfish jam from SpongeBob. Okay. You take a gazillion of these babies, put them together, and they're going to form the cell membrane. Now, to talk about how it does that, we need to first think about, I want us to think about salad dressing. All right? Let's think of a bottle of salad dressing. I think I want a different color for that. I'll go with this. All right, well, let's say that you've got this jar, or I don't know, bottle of salad dressing, whatever. I'm gonna leave the top open like this. I'm gonna have all this up here. And don't be thinking I'm talking about creamy dressing or gorgonzola dressing or Thousand Island dressing. I'm talking oil and vinegar Italian salad dressing, where the oil floats to the top and the water, you know, and the vinegar and the spices, whatever, are at the bottom. All right, and then you get this little meniscus line in between the two of them. You know, oil and water don't mix. They don't like each other. They will eventually separate no matter what. So the oil's going to float to the top, and the vinegar and oil and spices are going to float to the bottom. Think about what would happen if we put our little phospholipid friend with its polar head, its hydrophilic polar head, and its hydrophobic tails into our salad dressing. Where would it go in our salad dressing? If it's hanging out in the oil, the hydrophobic tails are like, oh man, we love this oil. We are hydrophobic, we hate water. There's no water up here, it's just nothing but oil, right? So they are happy. But the polar head is like, screw this, I am really bummed. I'm making a sad face because I'm a polar head. I'm hydrophilic and I am miserable out here in this oil. I hate it. We hates it, precious. So this is not gonna work. That's not gonna work at all. Because even though the hydrophobic tails are happy in the oil, the polar head is miserable. So that's not gonna work. So we gotta get rid of that, including that frowny face. All right, but if we put it in, if it goes into the water, I'll draw it a little bit bigger. If it goes into the water, the polar head is like, oh, I'm so happy. This polar head, it loves the water. It is hydrophilic. It's going to be very happy in the water. But these hydrophobic tails down here, they're like, man, we are hydrophobic. We're like mixing oil with water. We hate water. They are miserable down here. They hate it. Now, this is the part of class where I would ask you, you know, how can this phospholipid exist in salad dressing? If it's in the oil, the hydrophobic tails are happy, but the polar heads are miserable. If it's in the water, the polar heads are happy. And we're back from yet another spam phone call here. I'm going to continue this lecture and hope for the best that I don't keep getting spam. Anyhow, this little phospholipid is miserable up in the oil because even though the polar heads are happy, even though the hydrophobic tails are happy, the polar head is miserable. Put the whole thing in the water, the polar heads are like, yay, I'm happy, I'm hydrophilic. And the hydrophobic tails are like, get me the heck out of here. So none of this works. This problem has a solution. And this is the part of lecture when I would ask you guys to brainstorm about how to do that, but I can't hear you right now because I keep getting these spam phone calls messing up my screen recording. So what I'm going to do is erase this because it's not happening here. They can't hang out in the oil. Hydrophobic tails can hang out in the oil, but the polar head can't. And this doesn't happen here either, because even though that polar head is happy down here, the hydrophobic tails are miserable. But there's a solution. Where there's a will, there's a way. The hydrophilic head, the polar head, is happy in the water. But if we put the tails down here in the water, they're going to be miserable, so we got to get rid of that. But what if they go like that, with the hydrophobic tails hanging out in the oil? They love it. This is a solution. The hydrophobic tails are happy because they're pointing their feet up into the oil, and the polar head is happy because its head is down here in the water. Now, if I put another one of those in, the same thing's going to happen. The polar head will be in the water with the hydrophobic tails being all happy in the oil. And another one's going to line up like that, and another one, and another one. You see where I'm going with this? Let's get rid of the salad dressing. I do love technology, but I don't like phone calls while I'm trying to screen record. Anywho, a whole bunch of these line up to form your cell membrane because inside the cell, the inside of the cell is very watery. There is a ton of water in the cytoplasm of the cell. And so all of those polar heads will line up facing the watery interior of the cell with those hydrophobic tails pointing away from it. Yeah, I'm going to draw it. What the heck? Let's just draw the whole cell. I'll draw all these polar heads. And now my phospholipids are getting a little messier. But they'll basically form a barrier with the polar heads facing the watery interior of the cell and the hydrophobic tails pointing away from the watery interior of the cell. Let's get rid of this stuff up here, shall we? All right, but there's a problem still. Outside the cell, the cellular environment is also very watery. There is a crap ton of water outside the cell. There's water everywhere. And those hydrophobic tails are like, get me out of here. I'm miserable. I can't be near water. This is making me miserable. There is a solution. This problem has a solution because we have cell membranes. And those hydrophobic tails here are not miserable, okay? Because, and this is where I would have you all brainstorm this in class too, but because you're all not here, we can't do that. But what happens is that a second layer forms with the polar heads facing the watery exterior of the cell, and those hydrophobic tails pointing inward, facing the hydrophobic tails on that inner layer. So kind of like this. I'm running out of space here. Running out of space here on my tablet. But what the heck, I'll draw it like this. Oh my God, I have never had so many spam calls come in to my phone in such a short period of time. Remember when we were talking about Murphy's Law? If things can go wrong, they will go wrong. Well, that's kind of the story of trying to record this lecture. Lucky you get to hear all of these spam calls coming through, because I'm just trying to get this done, and I'm thinking I don't need to block calls right now because, okay, I just got one spam call. I'm not going to get any more. And then another one comes in. Anyhow, what happens is that you have an inner layer of phospholipids and an outer layer of phospholipids. We call the cell membrane is what we call a phospholipid bilayer. Oops, bilayer. You have an inner layer with the polar heads facing the watery interior of the cell, H2O, and the hydrophobic tails pointing away from it, and an outer layer with the hydrophilic polar heads facing the watery exterior of the cell. This is outside cell. And those hydrophobic tails pointing inward. I want to point out that the hydrophobic tails are not touching each other, all right? They're just hanging out together. And what you do is you get this whole hydrophobic region in here, all right? They're not covalently bonded to each other or anything like that. Let me just draw it down here, all right? So you get some phospholipids going like that. Now my little phospholipid drawings are getting much more primitive. All right, draw my polar heads here. Oh my gosh, this is absolutely ridiculous. Next time I do this on my iPad, I am going to turn off all notifications for everything, because now you're seeing all this ridiculous stuff. Spam. Anywho, we have a phospholipid bilayer right here. This whole thing is called a fluid mosaic. A mosaic in the art world is like a portrait or a piece of art that is made by putting together tons of tiny little pieces. So like a mosaic tile piece of art. And this mosaic here means many parts. Many parts making a greater whole. And we have many, a gazillion phospholipids making up the cell membrane. Fluid meaning it's not rigid. Not rigid at all. All right, so it's a fluid mosaic. We say that it's like olive oil. It's like your cell membrane is like a layer of olive oil protecting the insides of your cell, keeping the insides of the cell in and the outsides out. But I want to show you a little something here. And for that, I'm just going to erase just a couple of these here. And say, remember when we were talking about the difference between a saturated fatty acid that would be straight because it all has carbon-to-carbon bonds, and an unsaturated fatty acid that would have a bend to it? You can have phospholipids where they'll have maybe one saturated fatty acid and then one unsaturated fatty acid that puts a bend in it. Can you see that it makes a little bit of a gap in the cell membrane? It does. And so to prevent your cell membranes from being full of holes, basically, your cell has something that will take up that space. So for that, we need another molecule. Let's go with green here. And that molecule that's going to take up this space is cholesterol. And the cholesterol molecule, oh gosh, it's this huge molecule. I'm going to draw it wrong here, but it's got 4 rings to it with nothing but carbon and hydrogen. I'm pretty sure this is incorrect in the drawing, but you'll get the gist. 4 rings, nothing but carbon and hydrogen, and then just a little alcohol group down at the end. This alcohol group is hydrophilic, likes water. The rest of this is hydrophobic, hates water. But this whole thing, oh, you know what, I'm not going to draw it like this. I'm going to draw this ring end just like a circle, like that. All right, so we'll draw it like a circle like that, and then I'll have the little OH group off of it. This thing fits right in there. And the hydrophobic part will hang out in here, and the little OH group will stick out. Cholesterol helps fill in the gaps in your cell membrane, and we say that cholesterol, move it down here, cholesterol helps maintain membrane fluidity. Cholesterol helps maintain membrane fluidity by taking up space in there. All right, so I think that's enough to throw at you all at once, especially with all these spam calls coming in. And I think if I keep talking anymore, this is already the third time that I have had to record this because I had some problems with recording. I couldn't get my microphone on, and I recorded an entire 45 minutes worth in basically with no microphone on. Oh my gosh. So I'm not going to press my luck with the spam calls here, but I will end it here, and we will pick up where we left off on Thursday, October 3rd. But remember, October 1st, let's go back to a happy color. Let's go with purple. We have exam 1 on Tuesday. All right, I will see you all then. Study hard, and we'll pick up where we left off then. Have a great week. Bye-bye.